Hello everyone, and welcome to our first presentation in this new unit. Now, this unit's a little bit different than some of the ones we've done. It deals with a quantity, if you will, a concept that you use quite often in common English, but it's one of those that you may not really understand what it means from a science perspective, certainly from a physics perspective. And so in this unit, we need to lay some groundwork and some ideas and even some modeling techniques before we start getting into labs and actual situations. So I want to start out here by considering three little situations and the differences in those situations when something very important changes. So consider the following. Got this nice, friendly, studying student and a large, heavy ball. Now, ball just sitting there, student studying, no big deal. But clearly, something is different about the ball when it's moving. Consider our friendly studying student and a 5-kilogram mass. 5-kilogram masses, by the way, weigh about 11 pounds here on Earth, so it's pretty heavy. Right? If it's just sitting there on the table next to the student, no big deal. However, if we hold that mass above the student's head, clearly something is different. And our last little example, here's our studying student. And this is a little springy thing. Okay, you can grab these two ends and stretch it, if you will. Yeah, they used to be used a long time ago, really, to work out the chest. Right, so you could stretch these across your chest. Right. So right now, when it's just sitting there, no big deal. But now, when it's been stretched, and it's pointing at our students, clearly something is different. With me here. So what's different? Right? What changes when we set the ball in motion, when we hold the mass above the guy's head, when we stretch the spring and point it at him? Right? In every one of those cases, all three of those objects then have what we will call the ability to produce change. Right? They can produce change in themselves, or they can certainly produce change in the student. That's what we are going to call energy. Okay, we're going to define this quantity, energy, as the ability to produce change. It's an amount of ability to produce change. And this is kind of a nebulous, tough idea here, okay? Energy. It's one of those terms that you use all over the place, and a lot of times people use it without really even understanding what it means. Even more so than some of the ones we've learned before, like the difference between speed and velocity, right? One having a direction and one not. But energy is even a little bit deeper than that, right? So if something has the ability to produce change, it has energy. Now, for those of you who may have heard of energy before, you may know a different definition, one that's more of a physics textbooky kind of a definition. And that's not one we're going to use for a while. We're going to let that one slide because I don't really like that definition. I think it's easier to look at it as something that can produce change has energy. Now, there are many different ways to store that energy, all right, that ability to produce change. And the analogy I'm going to use here, not made up by me, but it's a really good analogy, is to think of it like money. Energy is like money that you bring to a bank. All right, so say you have a check for $100 from work, and you bring it to your bank. Well, you can store that money in several places. You can put it in a savings account. You can put it in a checking account. You could buy a mutual fund or a CD or put it in an IRA, right? There's lots of different places you can store that $100. If it's still $100, it's still money, right? It's just stored in different ways. Well, we can do that same thing with the ability to produce change, with energy. Right? We can store it in different ways. We have what we're going to call energy storage mechanisms. And three of them, mechanical ones, because we're studying Newtonian mechanics, right? But three of them are what were in my three examples, right, at the beginning of this presentation. So the first one was the moving ball, right? Because it was moving, was it producing change? Something that moving, producing change? Sure. Right? In fact, it's producing change because it's changing position. It's what it means to move, right? So a moving ball is changing position. Well, this has a special name. Everything does in physics. And some of you may have even heard of this before. It is called kinetic energy. Kine, remember, is the Greek prefix meaning motion. So this is quite literally the energy of motion, right? So something that's moving is producing change. It's changing position. Certainly if it runs into something, it can produce change, like in my example. Now, there are different symbols for this. We're going to kind of follow the way that we did this with forces, where all forces were capital F and the subscript kind of told you what kind of force it was. Well, all energy is going to be capital E because it is all just ability to produce change, right? The subscript will tell us how it's stored. Right? So the little k here stands for kinetic, motion, right? So E sub k. Now, you might see this as in like an AP class or something like that as a capital K or even a KE, all right? But we're going to use this kind of thing. And more, this symbol's becoming more in use, capital E with a subscript of a little k. Right? And eventually we'll have math models for these. We'll be able to calculate how much change is being produced. But for now, just want to talk about them as storage mechanisms. Our second example that I did was the mass. And when it was just sitting on the table, couldn't really produce any change. But when I held it above his head, then it could produce change. Right? And as you saw in the example, why? Because if I release it, it'll fall. And why would it fall? Because of gravity. And this one's a little different, though, than the moving ball. The moving ball was producing change because it was moving, right? It was already changing position. But if I hold the mass above the guy's head, is it producing change? No. But it could produce change if I let it go. This is that dreaded word you never want to hear, your parents talk about when they come home from parent-teacher conferences, right? This is a storage mechanism that we call potential. It could, just isn't at the time, right? And this one is called gravitational potential energy. That's a mouthful, right? That's E sub G. This is the energy stored because of where an object is in a gravitational field. Okay, we know that our idea is a mass creates a gravitational field around it. Any other mass placed in that gravitational field has a force put on it by the field, right? The field is the middleman. And we tend to think of this energy as being stored in that field. Okay, at least that's the classic way of looking at it. So gravitational potential energy. This is one of many potential energy storage mechanisms. Many of them we're not going to deal with. Okay, for example, in chemistry class, you deal with quite often what we might call chemical potential energy. Right? That would be, for example, the food that you ate for breakfast this morning had a lot of chemical potential energy stored in it. The gasoline in your car has chemical potential energy stored in it. Right? Under the right circumstances, that chemical potential energy can be stored as something else. Right? Under the right circumstances, we could take some of that $100 that's in savings and move it to checking. It's still $100, right? It's just stored differently. Same thing with our different storage mechanisms for energy. Okay, so this is gravitational potential energy, E sub little g, the little g, of course, for gravity. Now, the last one we saw was the stretched spring, and also works for a compressed spring, right? Why does that happen? Well, you know that when you stretch a spring, right, it wants to return back to its original shape. Right? It puts forces on things. Right? Forces cause things to move, and so it can produce change. But when, in the example, when it was stretched and pointed towards the student, it wasn't producing change yet. Right? It was potentially could produce change. Right? So this is another potential energy storage mechanism. But this one is named for objects like springs, rubber bands, elastic, things that will return back to their original shape. Okay? This is known as elastic potential energy, EE. You might see this as an S sometimes for springs if you're being specific, especially in an AP curriculum, but EE works for us, elastic potential energy. Okay? This is energy stored in an object due to its elasticity. All objects are elastic to one extent or another, and there's limits to that elasticity. Right? I can bend a meter stick a little bit and flick it and it would go back to its original shape. But if I bend it too much, it breaks. I've exceeded what's known as the elastic limit. Right? And then we end up with it not really being able to produce change anymore. Right? So there might be limits to these things, and we'll get into that more when we look at specific examples. But things, again, that are elastic, things which have a tendency to return back to their original shape, rubber bands, tennis ball, basketball, things like that, that can be changed, compressed, or stretched, and then they go back to their original shape, are said to store elastic potential energy. Well, those were the three examples we did before. But we have one more energy storage mechanism we need to deal with for mechanical systems. Okay? And this is going to kind of be a catch-all. Let's go back to our example of money being stored in a bank, because it's a good analogy for this. So you put your money in the savings account, you put your money in the checking account, you put your money in, a CD or something like that, right? And of course, when you use the bank, like when you go and use the ATM machine, right, what does the bank do to you? Right? Well, the bank charges you fees, right? Might charge you a couple of bucks for using the ATM. Well, those fees are still money, right? But that money that the bank charges you is no longer useful to you. Right? You can't get that $2 back from the bank and go out and spend it. Well, a similar thing happens in real mechanical systems. Sometimes we'll idealize them, right? But in real mechanical systems, there are charges to things happening. Think of something simple like a pendulum swinging back and forth, right? Probably played with something like that. If you let it go for a long time, what's going to happen? It's going to stop, right? Well, that means there was kinetic energy at some points, there was gravitational potential energy at some points, there was a combination, right, as it was going back and forth. But at the end, it's not moving, there's no kinetic. It's as low as it's ever going to go. We'll call that zero gravitational potential energy. So what happened to that energy? Well, we could say that like the money you put in the bank, it's gotten used up by these charges that are no longer useful to you. We're going to call this dissipated energy, EDIS. Okay? You'll see different ways of doing this. The concept builder guy uses internal energy, EINT, all right, down here at the bottom. I've even heard people call this E-therm, because quite often the energy gets stored as increased temperature. For example, rub your hands together, right? Rub them together harder, press them together harder. Right? You feel that thermal energy, right, in there? So those are charges to the bank, if you will, charges to you that are no longer useful to you. Right? Yeah, you can heat up your hands, but you can't take that and turn it back into food, at least not very easily. Right? So this is our kind of catch-all for all the things that happen in mechanical systems that end up reducing the amount of energy available for other mechanical things, right? Thermal energy, heat, right? Temperature change, light, sound, a deformation of objects, right? All those kinds of things. Now, if we were to study other areas of physics or chemistry, right? Well, obviously, if we study chemistry, thermal energy is one of the more important ones. We probably won't care much about gravitational potential energy when we're in chemistry class. Right? But thermal energy would become important. So we might pull that out as an energy storage mechanism and, put this one away. Right? If we study optics, well, that's all about light. Right? Probably don't really care there about stretchy things, okay, elastic potential energy, but light energy would be what is important, right? So this is kind of our catch-all, but the good way to think about it is like the charges that the bank gives you that are no longer useful to you. Now, there are many, many other energy storage mechanisms, right? But these are the ones we're going to deal with on an introductory Newtonian mechanics physics level, okay? You take other sciences, you take more physics, you take other areas of physics, lots of other energy storage mechanisms. So we go back to a guy here whose name might be familiar to some of you. Massive beard. James Prescott Joule, 1818 to 1889. He was the son of a family of brewers. Okay, they made alcohol, and he had an avid interest in the engines and things that they used in the brewery and in the thermal applications of what was going on inside of the brewery. Right, so he was really into energy from that perspective, right, and kind of both a chemistry perspective of the brewing and a physics perspective of the moving parts and the engines and the motors that they used, right, in the brewery. So he came up with a very famous and important experiment. All right, this isn't one we're going to try to replicate because it's really kind of hard to do. So I just want to talk to you about what he did here. This actually over here is a picture of his actual apparatus. It's in a museum. Okay, you can see this little thing here with all these little paddles on it, right? All these little paddles on it connected to this rod that goes up. Here's string that you can wrap, or rope that you can wrap around the rod, right? And it's got a crank on the top. And you can put this inside of this isolated container that you fill with water. So in this little drawing here, right, you've got an isolated container of water with this paddle wheel in here. And notice the rope goes over a pulley to some hanging masses. Now, think about what happens here. Right? When you release the mass falls because of gravity. It pulls on the rope makes this turn, which makes the paddles turn, which churns up the water inside of the isolated container. Eventually, it's going to fall all the way to the ground, and once it falls to the ground, it'll stop pulling on the cord will stop turning, the rotors will stop turning in the water, right, and the water will settle down. So we have gravitational potential energy getting stored as kinetic energy, but eventually, neither of either of those storage mechanisms remain. Right? The mass is on the ground, so it can't fall any further, so there's no more ability to produce change because of gravity. The kinetic energy stops, right? The rotors stop moving. So what happened to that energy? Right? Did it just disappear? Well, this was the brilliant part and kind of the chemistry part of this that Joule did. See this thing? That's a thermometer. So James Joule stuck this thermometer into the insulated container to measure the temperature of the water. If you think about it, when you churn up water, what happens to its temperature? Its temperature increases. And being a chemist as well as a physicist, didn't want to do that. He used this equation, and you don't need to know this equation, all right? It's a thermodynamics equation, which you do learn in chemistry, but it basically says an amount of thermal energy can be calculated by taking the mass of the water times the change in the temperature's water times something called the specific heat. The specific heat is the amount of energy it takes to change the temperature of the water 1 degree. Okay? Again, if you don't know this equation, that's okay. Just as long as you realize that it exists, right? So James Joule was able to take that temperature change, plug it into this equation, and calculate an amount of thermal energy. And guess how much additional thermal energy there was now in this insulated container of water? The exact same amount as there was gravitational potential energy at the beginning. So what he discovered and proved, right, was that the gravitational potential energy and eventual kinetic energy of movement didn't just disappear. They just got stored as an increase in thermal energy, or what we would call dissipated energy. Right? The energy was dissipated, but it didn't just go away. See what I'm saying? So this was a huge thing in science, because they really didn't have an idea of where did the energy go when mechanical systems would eventually wind down to nothing, right? When they would stop, no matter what the mechanical system was. And it would just eventually, it's going to stop unless you keep adding things to it, right? So why would that happen? Well, Joule said, that energy didn't disappear, it just got stored as something else, right? It was charged to our dissipated energy account, and it's still really there. This is a super important idea. It's called the law of conservation of energy. Okay? And conservation has a very kind of different meaning all right, then we use it traditionally. Traditionally, if you say you conserve a resource like paper, like we do here at the school, right? We conserve paper by reusing it, right? So we recycle it, it gets turned into something else, right? Well, conservation in science, when a quantity is conserved, it means that the total amount of the quantity doesn't change. If you've had chemistry, you might have done some experiments on the law of conservation of mass. Right? The mass of the reactants is equal to the mass of the products if you keep careful count. Right? Conservation of mass. So the law of conservation of energy is stated that in any isolated system, we'll talk about what that means, the total energy remains constant. It is conserved, in a word. Okay? This is one of a couple of different conservation laws we're going to learn about. We learned about a third one in APC, so 3 total. And there are other conservation laws, like we said, the law of conservation of mass. But this is a big one, a really big one for us here in our energy unit, and kind of our big idea. Okay? Now, a key thing here is the first part of the sentence. This only works if it's an isolated system. So what does that mean? Well, if we go back to this device of James Joule's, right, the water was inside of an insulated container, right? So, like a thermos. Keeps hot stuff hot and cold stuff cold, right? So that way it wouldn't heat up because of a light on it from the outside, but it also wouldn't let any thermal energy go out that we couldn't keep track of, right? So we had to keep everything kind of closed, isolated, if you will, in order to be able to compare everything, okay? So in a mechanical system, which is pretty much what we talk about in here, isolated means there are no external forces. And by that I mean that we're going to have to define a system here. Okay? We're going to talk about what objects are inside and what objects are outside of our system. All right? And an external force is a force which comes from outside. Right? It is external to our system, as opposed to things that are inside. So in our Joule example here, sure, there's forces between the Earth and the mass, right? Force of gravity. There's a force between the mass and the string. There's a force between the string and the rod, right? And then there's forces inside of the container with the rotor here turning and pushing on the water, right? But all those are internal forces, because we're going to look at this whole thing, right, as an isolated system. There are no forces from outside. Now, there could be. He gave a part of his apparatus for this. See that? Right? If you reach in there and crank that and stir up the water, you now no longer have an isolated system. Right? You have got an external force, you churning up the water. Right? So you can see here, this whole definition of our system is going to be super important. We're going to get a lot of practice in that as we go through this unit. But this is our big idea. If our system is mechanically isolated, if there's no external forces, then the total energy remains constant. And so we can compare one point to another and use it to make predictions about things. Now, this is probably how you've heard this being said before. Energy cannot be created nor destroyed, right? That's the more traditional way of saying this. I'm not overly fond of that, kind of like I'm not overly fond of the traditional Newton's third law statement, because what it leaves out is this, right? That we got to be in an isolated system. Right? So if we're looking at a system that's not isolated, well, then the amount of energy in there, in that system, can be changed, right, from outside. So got to be a little careful here. This also is a little bit iffy because of how we now deal with mass, right, and energy mass conversions, E equals mc squared, right, Einstein stuff, general relativity, and how we can have mass become energy and energy become mass, right? Nuclear explosions, for example, right? Nuclear reactors end up with enriched uranium or plutonium, and it becomes smaller elements, and the total mass actually decreases in the process. And where does that mass go? Well, it becomes energy. Right? How much energy? E equals mc squared of energy, where m is the amount of mass that changes, and c is the speed of light, which is a very large number, 186 million miles a second, 3 times 10 to the 8th, 300 million meters every second. Okay, so And then that's squared, right? So it's a lot of energy from a very small change in mass. So I kind of like this definition a little better, even if it's not nearly as pithy, if you will. But you're very welcome. Now, this is a big idea, and it's going to kind of govern the entire unit that we're doing here. Watch this little movie about it, too, just very short.
James Prescott Joule gets credit for discovering the law of the conservation of energy. He wasn't the first to explore the region,
and the thermometer.
But like Columbus, he returned with maps that,
Churns up
from
the
then
water.
onward, the rest of the world could
Temperature
follow
goes
with
up.
confidence. The son of a British brewer, Joule studied the efficiency of steam and electric engines for the family business. He devised an ingenious method of measuring how much mechanical energy turns into heat. A large weight, lifted to a certain height, has a precise potential energy, mgh.
Don't worry about that math model, we'll get there.
Joule arranged to have falling weights turn paddle wheels inside a carefully insulated container of water. Then, he measured the water's temperature. In this way, Joule showed that a given loss of potential energy always turns into precisely the same amount of heat.
So the total amount of energy did not change. Right? That's our big idea. If you have an isolated system, right, then the total amount of energy remains constant. It is conserved.